So, you know, people always worry and say, okay, well, you know, the end of the sun is in about 4.6 billion years when it runs out of hydrogen. In the process, as we will discuss in detail, it will swell up in stages, first time roughly to the orbit of Mercury, which is the planet closest to it, at about 40% of the distance between the Earth and the Sun. And then in the final red giant stage, it would swell up in size when it becomes full red giant roughly to the orbit of Mars, perhaps swallowing the Earth in the process, right? If the distance between the Earth and the Sun doesn't change for some reason that I'll discuss later when we talk about it, then certainly it would engulf the Earth, right? But we don't have to wait that long, 4.6 or so billion years, for the life on Earth to become impossible. Things will get quite hot much sooner, in half a billion to a billion years, when the Sun will be so luminous that all of the water on Earth would vaporize. Now, in the past, there's one thing. I mentioned that the Sun was 30% less luminous when it became a main sequence star than it is now. And when this will happen, the luminosity will go up maybe by 10%, not as much, not as big a change. So you can say, well, if the Sun was 30% less luminous in the past, how come we have fossils of living organism on Earth that are 3 to 3.5 billion years old? There had to be some kind of compensating mechanism to increase the temperature on the Earth in spite of the reduced luminosity of the Sun. And one possibility is that when the Sun and the planets around it formed, there was initially on terrestrial planets like Earth a period of very intense volcanic activity. All the gases trapped inside the planet were coming up to the surface. And most of those gases, including the water vapor, methane, carbon dioxide, and others, are so-called greenhouse gases. They trapped infrared radiation. And this trapping causes the atmosphere to warm up. So although the Sun was less luminous, there was this compensating greenhouse effect produced by volcanic gases that kept temperature high enough for these first forms of life to form on Earth. Okay? Now, it is not clear to me, at least, that there is an equivalent compensating mechanism that will keep the Earth cooler when the Sun become more luminous. I can't think of anything that would actually reduce the temperature on the Earth, unless we somehow manage to in some way block the incoming radiation. Okay, but this happens to all main sequence stars regardless of their mass. Okay, so there are different parts of life of a main sequence star like Sun, contracting protostar. Just before it becomes a main sequence star, it goes through a period of instability, producing these so-called bipolar flows that I haven't discussed. Then it will go through the first red giant stage, where it will swell up to about the orbit of Mercury. Then the core will get hot enough so that helium in the core, because all of hydrogen has been converted into helium, will now start fusing into carbon with the production of energy. But that is short-lived. Eventually, all of the helium is burned. The star wasn't massive enough to start fusing heavier elements, heavier than helium, carbon, and so on and so forth. It swells up into the last red giant phase, when it will reach the orbit of Mars. And eventually, the pressure that is built in will push out the top layers forming so-called planetary nebula, and what is left behind is dead core, non-fusing core consisting mostly of hydrogen and some oxygen nuclei. And it will stay on the main sequence for another 4.65 billion years. Eventually, all of the hydrogen in the core will be used up. All of it will be fused into helium. And then what happens is that the star enters the first red giant stage. It swells up. It is not massive enough to start fusing helium in the core into heavier elements like carbon, but eventually it will do that when the core gets hot enough. And during this first red giant stage, it will expand perhaps to the orbit of Mercury, a planet closest to the Sun, at about 40% of the distance between the Earth and the Sun. Eventually, the helium core is heated up to about 100 million degrees Kelvin, and then the helium ignites. Carbon is being formed through the fusion of helium nuclei, and then the star enters this so-called yellow giant phase, which lasts maybe 100 million years. Eventually, all of the helium in the core is fused into carbon with admixture of oxygen nuclei, and a star like our Sun is not massive enough for its core to get hot enough so that now carbon can fuse into more heavy nuclei. And basically that's the end. It swells up again, final red giant stage. It will reach perhaps the orbit of Mars at 1.5 times the distance between the Earth and the Sun. And the thermal pressure that builds within will push out the top layers, forming so-called planetary nebula. And what is left behind is very hot and very dense, dead in a sense that it's not producing energy anymore, carbon core, making what we call a white dwarf. Okay? Let's look at different steps in this final stage of the life of a star like our Sun. So, as I said, eventually, in about 4.5 to 5 billion years, all of the hydrogen in the core is fused into helium. Okay? So that will happen in about 4.5 to 5 billion years. The Sun doesn't have enough mass to actually ignite the helium, to make helium fuse into heavier elements. Okay, so this helium core initially does not produce any energy through nuclear fusion, but it's contracting under its own gravity. Okay, and as it contracts, it gets hotter. The structure of a star at that stage looks something like this. Okay, so here we have contracting and heating helium core. Okay, so just like in the case of a protostar, what is happening here is that the gravitational energy of a contracting core is transformed into thermal energy. Okay, and when it gets to be hot enough, then hydrogen is fused in this shell surrounding the shrinking helium core, and because the high temperature of the shrinking core, the fusion in this shell surrounding the core produces more energy than the fusing core of the sun while it was on main sequence. So here we have a shell of hydrogen fusing into helium with release of energy. And then we have top layers of hydrogen, about 75%, and helium, 25% gas. Okay, so this here illustrates on the left the cross-section of the sun while it is on the main sequence. It has hydrogen fusing core. Its radius is about, right now, about 20% or so of the sun's radius. And then the top layers of hydrogen and helium. Now, when the sun enters this first red giant stage, what it has a dead, that is a core that is composed of helium, but it's not hot enough to for the helium nuclei to fuse into heavier ones with the release of energy. However, the fusion proceeds in this hydrogen fusing shell that surrounds very hot and shrinking helium core, right? And then we have the top layers of hydrogen and helium gas. Okay, so as I mentioned earlier, the temperature of contracting helium core is very high, and therefore the rate of hydrogen fusion into helium in that surrounding shell is very high. It is higher than the rate of fusion in hydrogen core while the sun was a main sequence star. So this high rate of energy production creates a tremendous pressure that pushes out the top layers of the star. Okay, and the star expands. As a result of this expansion, the surface will cool because now the surface is at a greater distance from the region where the energy is produced, from the shell surrounding the shrinking helium core, right? Just like when you, if you have fire going on in the fireplace, right? If you are close to it, you receive a lot of energy per unit area, right? But if you are farther away, the temperature of the air drops from the greater distance from the source of the heat. So the same here, as the star expands, these top layers being pushed out by increased thermal pressure, their distance from the energy producing region increases, and as a result, the temperature drops. Because of the drop in the surface temperature, the color will change from what it is right now, yellow-white, to orange-red. First, the luminosity of the star increases because it produces more energy than it did when it was on the main sequence. And the second thing is that the surface temperature drops, and therefore the color of the star changes to orange-red. So because it's swelling up and looking red, it enters its first red giant stage. So in the case of the sun, as I mentioned earlier, its radius would be about equal to the radius of the orbit of Mercury. And this stage would last for about 1 billion years. 10% of sun's life on the main sequence for 1 billion years. Eventually, this shrinking and heating helium core will heat up to a temperature of 100 million degrees Kelvin, which is high enough for the helium to start fusing into carbon. Now you can ask the question, why is higher temperature needed to fuse helium compared to the temperature needed to fuse hydrogen? Well, the thing is as follows. Let's look first at the hydrogen fusion. We have two protons, essentially, heading toward each other. Each proton has a charge, positive charge, equal to the charge of the electron. And like charges repel each other. So these two protons heading towards each other are repelling each other with electrical force. So for them to get close enough to each other so that they can bind via strong nuclear force, which is 100 times stronger than the electrical force, but it's very short range. It acts over roughly the diameter of the proton, or say few protons. So these two protons have to get really close for them to be bound by the strong nuclear force. And to get close enough, in spite of repelling each other, they have to be moving with a high velocity. And it turns out that for protons, you get a high enough velocity if their temperature, which effectively measures the average velocity of the particles, is about 10 million kelvins. Okay, so now let us look at the helium fusion. So now we have two helium nuclei, helium-4 nuclei, which consist of two neutrons and two protons heading towards each other, right? And they also repel each other with the electrical force. But now each one of them has twice as much charge. This one has the charge 2 times E, and this one also has charge 2 times E. And it turns out that the size of the force of electrical repulsion in this case is proportional to the product of the charges carried by the nuclei. So here I have 1 times 1 in the units of E. I have 1. Here I have 2 times 2 in the units of E. 4 times. Okay? So the force of electrical repulsion between helium nuclei is 4 times that in the case of protons, hydrogen nuclei. So clearly, because of now larger repulsion, 4 times larger repulsion than in the previous case, they need to be moving at much higher speed compared to that needed for protons, so that they can get close enough and be bound by the strong nuclear force. And for that reason, we need, in the case of helium-4, a temperature of at least 100 million degrees Kelvin. Right? So in the case of helium, it's 4 times this one here. Okay? So as a result, the higher temperature, 100 million degrees Kelvin, is needed for the fusion of helium to take place. And as you go to progressively heavier and heavier elements, to say fuse carbon into heavier nuclei, you still then will require higher temperature, because those heavier nuclei have larger positive charge. Therefore, they repel each other more strongly, and you need to bring them together with a higher speed so they can get close enough in order to fuse. Now, more massive stars, they have enough mass so that this helium core ignites right away, right? It's already hot when it's formed, that the fusion starts right away. In less massive stars, like middleweights, like our sun, there is a pause. There is this first red giant stage where the helium core is shrinking, heating up, but it's not fusing yet. And when its temperature gets high enough, then it will start fusing into helium. The fusion of hydrogen into helium proceeds via a so-called triple alpha process. Alpha because another name for helium nucleus is alpha particle. When people were studying radioactivity at the end of the 19th century, beginning of the 20th century, they realized that there's these particles that carry charge twice as large as proton, but they didn't know what they were, because at that time helium was not identified as a chemical element on Earth. Remember, those of you at least who took astronomy 1P01 will recall that it was observed for the first time in the spectrum of the sun. Hence the name helium, because in Greek, helios is the name for the sun. Okay? So alpha particle and the nucleus of helium are one and the same thing. Okay?